tutorials. And yeah, I was able to run it on my private computer, but I was trying to run it on the Fermilab computers, and I was not able to source the Centaurus workbench. So I was wondering if there's some guide how to how to source or licenses and the software itself.
Sure. So okay, depends a bit how you have your installation, obviously. So you install the software locally on your machine, or you?
Yeah, we
So
have some local cluster where we have like installation with few licenses, but I believe that it's a bit outdated. So the software is working, but it's a different version. I would ideally would like to work on the Fermilab where I have the latest version and everything compatible with others.
Sure. So I mean, normally the best way, I don't know, I don't know the system in Fermilab and such, but the best place to have it, it's some kind of CVMFS or I can tell you what we did at CERN. So we had an installation on CVMFS. You have to be careful with regulation. Obviously it shouldn't be a folder that everybody has access to and such. So that might need a bit of IT help, to have some place. And as I mentioned before, especially if you want to use a cluster and use these resources, you would need that these cluster nodes can see the license server and can see the software, obviously. So it can source the installation itself is simple. So I mean, you can provide the binary. So normally, if you have the license and such, whoever did the purchase should have an account with Synopsys, and you can go there, download the latest. Depending on the status of your license, but if you're paying and everything, you should be able to download the latest version of the binaries and do the installation. And it's rather straightforward. You just make sure you install the Centaurus tool because it's asking you about multiple tools, not only multiple Synopsys tool. And then in there's a setup script, like a little bash script called setup.sh. I will show a bit. I can show actually how I do it locally. And then once you source that, you should be able to run the software. Then the license, as I said, is the same. So if you add the license in the little local like LM manager or whatever, like license server, the best is to have it at the site level. So at CERN, I mean, there's one in microelectronics, they have a license server for all kind of things. So they added, the Xilinx, for example, the Xilinx tool are often is the same tool. So you could have these licenses hosted by the same people hosting FPGA software or microelectronic design software. And that's what you need. Essentially, that you can connect to these two things and set the environment variable for it.
Yeah, so maybe it would be possible, to add some information on the Twiki. I mean, basically for the Fermilab servers, I think the server is called FASIC Beast 1 and Beast 2. So I'm not sure, if anyone here is from the Fermilab and have the experience with that. It would be great if you can share that.
Pam is the person who manages the licenses for the ASIC group. So it's probably best to contact her if you're having issues.
Yeah, you should write an email to Pamela Klabbers, KLAB. Is that two B's? 1 second.
Yeah, I know. I was in contact with her. She set up an account on that computer, but she didn't know about some guide how to start the Centaurus TCAD. So that's why I'm asking.
Well, so what I can do, let me try to share my screen. So I have this time the software in the live computer. So I can show you how I set up my things. Maybe that can help a bit. Maybe sometimes it's just a little detail. Let me share. There you go. So I guess you can kind of see my screen here.
Yeah.
Good. Okay. So I have a PC here where I have actually a bit as you did. So I have the local installation of the TCAD software. And usually I always set things like that. So I have a little setup script, a bash script. And then there's essentially 3 lines you need to start the software. You need to know where the binaries, so wherever the tool, in that machine that you mentioned, if they have the tools already, there's probably a folder, and you just need to know where the binary is. It doesn't have to be a folder that you can write in. It just has to be a folder that you can read in. You need to tell him the LMD license server location. In my case, this is in Kansas University, so we have the license server there. And you need to give it a home folder, so a folder, an empty folder that you're gonna put your projects, that you're gonna download the examples and things like that. So normally, then each time I just log in, I just set this up, and normally then I'm good to go. So as I mentioned in the previous tutorial, the command to start the software SWB. And normally, if you have a valid license and everything goes well, so you see the little prompt here. It will complain here in the console if you have a problem fetching a license for some reason, or it cannot contact the license server, or if one of these variables is not set, for example, the home folder, it will tell you, oh, okay, you need to set a home folder, or it's going to default to some to your home, essentially, which is. But if everything goes, it's a bit slow because I'm in between multiple computer hopping. You have the centerless workbench, which I mentioned last week. So you have the structure that I described. So now I have no project loaded, but I have preloaded here a few of the examples that are from the repository that is on the website. I will go through one of them just to kind of dynamically show you the various aspects that I presented last week, and then after that I can maybe go back to the slides. We'll talk a bit about device generation and device simulation, and then we can come back in well, maybe not today, but towards the end, coming back to these examples and try to understand how they're built and how you can obtain results. So you have on the project view here the various examples that I mentioned last week. So for example, you can just explore the hierarchy, FinFET, it's quite fancy simulation you would have here. So you see that, for example, 10 nanometer, 14 nanometer, 22 nanometer. So this is a bit, and that's why I like to provide these examples. These are a bit outside of the if you're a physicist wanting to look at the detector, these are really CMOS oriented. But if you're into design, or you want to look at design structure, for example, for diodes, for small diodes, for CMOS process, for maps, for example, it might be worth to look at the set of example for CMOS processing, for example, bipolar processing, that are also good examples. So for here, I would just use one of my scripts. So you have a project, so I can double click on it, and it will load my hierarchy. So as we mentioned last week, so we have multiple tools. So the first thing we do is what we call the device editor, so SDE, which is building diode. This is a diode with like a few stripes, actually. So it has 3 stripes or 3 strips. And this is one of the parameters that I said we could modify, or that we can use to drive the simulation. So everything is right-clickable on. So you can right-click on this, and you get a little contextual menu. You can look at the property of this tool, for example. It would tell you more about what's going on here. So it's as a title, here title is Diode 2D. It is associated to one of the tool. In this case, is the Center's device editor. You can click here, and it shows you the family of tools that you can use and then integrate there. So you can just click, and it's gonna pick that tool. So you have processing, device editing, electromagnetic wave simulation, quantum simulator, etc., etc. You have a lot of fancy tool, the visualization tools, spice tools, and kind of scripting tools. So you can also have, for example, Python script or whatever, something completely custom, some TCL, Bash. There's a few different language implemented there, so you can also put these tools in there if you want to do processing of files or move files around and things like that. Then it tells you the command it's going to run, and then you can look how it's going to label the input and the output of this simulation. So it's kind of a patterns for the input file. It will receive a file. If it use any input, you can kind of tell him that it will take a file, and this keyword here, node, essentially tells the tool to look at the previous node, so in the hierarchy, to go back in time and look for nodes with that the previous node that attached to that process. So, for example, if you make a device, and then in the second step here, which is going to be the device simulation, we have 4 different simulation. They all link to this parent node here. So this will take the number of this node and replace it when executing real simulation. Was clear. It's a bit complicated, but I will explain a bit more after. And the same for the output. So in that case, depending for the type of output from a command file, the different plotting and output file that can come out from the different simulators. Essentially, they just have like a fixed syntax with different suffix and are attributed the node number of the real simulation node that's going to be running, like these yellow boxes here. And then you can, this is quite advanced, but you can fine tune parallelization. So if you're running in a machine, you have multiple processor or you have multiple things running together, you might not want to launch and use all the RAM and all the CPU. You can fine tune things. Then you have let's say if you right click here, you also can edit the templates that are going to be your input. So normally the one that always needed is a command. So if you go to edit input command and the file doesn't exist, it's going to create the file. Otherwise, it's going to open a script that the one that we have defined already. So it has the name of the tool and the suffix that's being set in the tool parameterization that I was showing before. And here we have a simulation script. So I won't go into detail just right now because it's quite explained more in detail in the slides. But you have essentially a scripting language that exists for the device editor that allows you to script the building of a device from the geometry to the doping profile to the contacts, depositing metal like copper and aluminum, defining them as electrical contacts and such, and outputting all that at the end to the tool. What is interesting to note here is my parameter. I'm trying to find a good one here. So in my script, so this is how I parameterize my script. So everything, that script could be completely executable if I define numbers everywhere. But as I mentioned in the tutorial last week, it's interesting to be able to make things parametric when it's easy, at least. So you can control it with the tool and change that parameter if you want later. And the way you do that in the script is you have these @ with the name of the variable. And then when the nodes are being generated, these will be replaced by the real values. I'll close this for now. And so now we have the node. So they always start with one of these like empty nodes. So this is the empty simulation, essentially. And then that kind of inherits all the link from the real nodes. So in that case, we have one parameter. So we want 3 scripts in our detector. So that becomes the real node. So in that case, I executed it. So it's done. You have the color scale of the status of the nodes here. So because I ran everything, so we don't have to wait for the simulation. So I can click on that node, and actually then you can double click. And then you're gonna have, as I mentioned last week, the node explorer that is gonna pop that will allow you to see what happened in that simulation. So you have all the files that I mentioned, and now we can see this is a real node, right? So it's node 7. So now the file was generated as node 7.dbs, which is device simulation in that case. And then we can see the script. So this is essentially the script that I defined earlier, but then the numbers, right, that I had in at has now been replaced by the number. Then you have the error, so there was no error during execution, so there's nothing in there. This is the kind of the job submission output, and then the log of the simulation. So this is going to be kind of the commands that have been executed. The output, so this is a bit more verbose. So if you are debugging, you're going to be looking at that. So you're going to add really all the verbose of the tool, what happened, if there's warning and such, what was called, how much time it took, etc., etc. You know, submission data, local submission error script. In that case, this is another common file being generated, so it has its own log. And the final result, it's usually these TDR files. So these are the files that along all the simulation are going to be representing your devices. And so these are plottable, and we can look at them. And actually you can just double click on it. So that I will show something here that is very annoying. It's happening for me. So double click, and you might have the same problems. I think it's good I spend a second on that. So when you click on a file here, it will kind of try to pick the best editor for it. So if I want to open this guy, I can double click, it's going to open Git, and then just show me the file and Git. So for the TDR file, it knows that it should be associated to the SVisual tool. So if I double click, it starts the SVisual tool and opens my device. So this is the SVisual tool you're going to be using to plot devices and such. The problem is I'm connecting through SSH tunnel, through a VNC, through a no machine. So I have I'm not physically connected to the machine, and this plotting software expect some kind of hardware acceleration for plotting. So there's a way to bypass that. But in that machine, I have not set that up, or the thing I have to do is to activate that manually by using the tool manually in the command line, which is a bit annoying. It's very nice to be able just to click and open the files. So most probably if you're running locally or on your setup, depending on the driver OS combination you have, you might not have that issue, but I have that issue on that specific machine, which has a bit rather older OS. But in any case, so worst case, I want to open N7 mesh, underscore mesh.tdr. In my case, I just go on the console. So I'm going to go to the folder where everything. So this is my home folder. So you see the different projects that I have imported. I'm going to go to diode 2D. And here essentially is just every file that were ran and input and outputs for every node of the simulation. So here from the command line, I can ask SVisual. So in my case, I'm using the -m option, which is the type of graphic acceleration. So it's specified the type of graphic acceleration. If I do -help, we get more explanation. So you can run in batch. You can run in batch with X windows. You can run in GLX, and in my case is the M Mesa driver is what is running. By default is using, I think, the GLX, but this is not working in my remote desktop configuration. So I'm going to do SVisual -m, and then it was node 7 mesh.tdr. So now I get the rendering of the colors, and I can look at my device, so we can interact with the device that we just generated. Can zoom on the pixels here, for example. So in that case, what we have is 3 pixels. and kind of a guard ring, so which looks like pixel but has a different metallic structure with a end doping under each of the electrodes and a P substrate. So in that case, this is just the device that came out of the device generation. So obviously the next interesting thing is to apply electrical bias and such, and to obtain electrical simulation results. What a few other things I want to say here. If you want to run a specific node, you can always right click on any nodes that need execution, and you can do run, and it will pop a menu. So that menu I explained in the tutorial last week. You can pick the different queues. You can decide how many of them you can have running, because you can also, for example, select, I want to run all these nodes. I can do, run, and now it picks the number of all the nodes. So it's going to try to run all that. He's going to try to run as many as he can with the number of licenses that I have. And the preprocessor is going to regenerate all the inputs from the parameter that are in the deck, and then try to run everything at the same time. So we're not going to do that because it's already being run. Another interesting thing, so this is a bit of demonstration of what I was talking about, the parameters. So here, if I right click, so I have different defined parameters. So in my device generation, I say, okay, I want a device with 3 or 4 or 5 pixels or strips. And the second, this is a device simulation. I want to do the IV of that device. And I want to do that for different level of irradiation. So I introduced a parameter called fluence. And this parameter, then I say, okay, I'm going to do a simulation for different fluences. So maybe my boss comes and say, okay, well, that's not enough. I want to have one more. So I can right click on this, and then I can add a new value to the simulation. So you see what the tool did now? It created this new branch, which is essentially all the simulation, this one, plus every other simulation as we have defined before, but for this new parameter of 110 to the 15. So you can see they are in white because they obviously not been executed, but it also populated the sub parameters so that we can run everything that should propagate normally. So it will take the same device, it has the same parents of all these ones, but then it becomes a completely new branch of simulation, and then it's like you just wrote 20 different scripts in a sense. If you double click on it, you're going to see there's nothing, absolutely nothing now. The reasons for that, it's not being pre-processed, which is also something I mentioned in the tutorial last week. So that means nothing was done. And the only thing it did is populating this grid here. So pure processing needs to be done. So you can right click on it. You can do pre-process. I was going to ask you if I want to save. I say yes. So you get this little execution script here. Essentially tells you what it did. But now I can double click here and I can see the script. Essentially that has been generated with all the parameters in, with the irradiation. If you look at the irradiation model here, so this is the definition of the traps for the irradiation model, which is calculated from the fluence. So there's some math being done, so you cannot see the value directly, but it's there to be run, some parameter file. So this is ready to run. So this is processing. So it's a bit tricky concept, but once you get it, it's very useful. And one last thing, only one or two last things. At this year, so everything after the end of your last processing. So in that case, this is my last tool execution. There is additional columns. And these are also parameters. They are output parameters. So for example, BVAK. Here is my breakdown value at K, which is extracted from our IV curve. So there's a little math tool that we can use that can extract a breakdown from an IV curve of a diode. So it would calculate this breakdown and essentially put in the grid there the values that has been calculated. Here's another example. So in the tool, there's a mathematical function that can find the maximum electric field inside your volume. So if you're looking for a breakdown, you want to know maybe the source of it and which position it was, what magnitude that it's reaching. So this is a tool that, in that case, in this example, it shows how we extract the highest electric field and the position in the substrate where it occurs. And the last one, the W0, is, for example, we are depleting a diode. So we're applying a certain bias voltage, and this extracts the depletion depth of your diode. So this is nice, just all done automatically. So as you generate new cases here, well, all these values will be calculated as well. And so you can look at the table and understand easier your simulation. Few more things. I think we're good for now. There's a lot more functionality to that tool, but I think for now, I will go more when we go back through this example and through the scripts. So for now, let me just switch screen. So you can see the right screen, I suppose. Okay. So for the next maybe 30 minutes, 45 minutes, I'm gonna be starting about talking about how to generate structures. I'm gonna show a few examples how I've done that in cases where we use the TCAD simulation to look at detector design. And I will argue about the different ways we did that and why we did that and what was interesting in the different approach. So first way I mentioned before, it's a very powerful tool. So you have in there the process simulator. It's quite complex. It can do quite a lot of things for you, and you can see around the pictures there the nice complex structure that you can generate. You can do it in 2D, you can do it in 3D simulation. Obviously, if you have the computing power for it. It has nice integration with modern modeling engines and libraries and such. It's quite performant. It offers all kind of in the synopsis tool. A nice thing is this what we call adaptive meshing. So the tool is quite aware of what it's doing, and then it will kind of by itself arrange your mesh to make sure that your devices variation are represented well, and so you will have smaller mesh elements like here where you have big variation, in that case in the doping profile or in the topology or in at the interface, for example. You will try to have smaller elements so you have more precision in the simulation, and the tool helps you a lot doing that. There's even APIs, even in Python, so you or in C++, so you can, if you're doing really detailed device physics, or people that are working with different materials that are not silicon. So I've seen people trying to do things with germanium or with heterojunctions or diamond. So there's a lot of data sets for a lot of material in there, but you can also implement your own, or even implement your own, let's say, impact ionization model, or your own implantation depth versus energy model or something like that. An advanced feature, but it's possible. And it has quite a lot of advanced physical model for if you're doing processing of devices. It can be very interesting. So you can look at analytical model for implantation, but also you can do Monte Carlo simulation. So if you want something more detailed, you can look at diffusion, or what you call annealing. So you do laser or flash annealing on your junction to activate them. And then you can push this to very detailed kinetic Monte Carlo models to represent the population of defects and dopant in your substrate. These tools are able to handle simulation of mechanical stress. So when you do, for example, you grow a bird's beak, like here, you're trying to create strain in the oxide, and this is an effect on the mobility of your carriers. This is handled by this tool when you do the growth of the bird's beak, for example. And then when you do all kind of bad oxidation on surfaces of PVC, also you induce stress, and this is handled by the tool. Just got a few slides here about the models. So if you're doing implantation, you might just want to do something like, it's a one-line command in test process. It can be very simple. You say, I'm going to do an implantation of arsenic. Here's a dose I'm going to give by a square centimeter. The energy in kV is going to be 50 kV. The tilt is going to be 7 degrees. So that means I'm not going to implant directly perpendicular to the wafer surface, but I'm going to implant with a 7 degree angle. Usually this is to avoid channeling, so you don't have really ion channeling inside the in depth in the silicon. And the rotation, so you can say usually the wafer can be rotating during implantation, so you can set this way, and then you can give yourself this verbose level. And you will get an implantation, but then you're probably not gonna get the most accurate thing. So in most cases, it's already fine. You can have a good agreement between analytical, so you can have like simple analytical models that describe an implant. These are parametric, so they're based on data, so they have different distributions. So just a Gaussian or more complex distribution like Pearson, Joule-Pearson, which are you have to look at the literature. These are ways to describe implant as function of that. And also they have analytical model that can do that in 2D and in 3D. And then all kind of things like screening. So if you, for example, apply a little layer of something on top of your silicon to slow down the ion to obtain a certain difference in profile, this is handled by the tools. It can calculate the damage, the damage introduction that you do when you do implantation. It can calculate amorphization that's occurring in a highly doped semiconductor when you do implantation. It can handle molecular implant like for example boron fluoride. And it has what we call calibrated implantation tables. So if you're targeting a certain process, for example, 80 nanometer, if you're doing some maps or something, there is calibration tables that have been, let's say there are fits of these models for a given process. So they have been measured and fitted, to target better. And this is good to look at when doing this kind of simulation. Then when you add dopants in your substrate, what you're going to do usually is you're going to be eating up your substrate so that your dopant, and that's true for CMOS detector, and that's true for CMOS circuitry or such. You want to activate your implants, so you're going to kind of eat up your substrate to move around these implants and defect and kind of combine them to get charge defects that you want, like interstitial or vacancies. And this is done usually by laser. And this is quite complicated. So I put the formula there. I'm not going to go into detail there. You can track essentially the diffusion, the recombination rate, the creation rate, and the divergence of these different defects. Now, if you treat them like point defects, and essentially what is done in the tool. And there's a hierarchy of models. You can go from something very simple, which works with standard implantation, which is true in most of a detector application. But if you go smaller feature size, or you go to higher implantation dose, or you want to look at more in detail what's happening, then you can go to real high level tracking of all these defects and their chemistry between each other, which obviously comes to the cost of a lot of computing power. Most interesting maybe is the etching and deposition. So even when you're building a structure, you from a geometrical point of view, you want to use these kind of tools because actually it's going to give you more realistic surface. So there's obviously all the things you can do in a geometrical level to a wafer. So you can etch in multiple ways, using different tools, or depending how you're working on crystal, or sometimes you can do just something, whatever you want for the fun of simulation, even something that's not physically possible. You have deposition models, so you can do isotropic, anisotropic deposition. You can do kind of fill or liquid-like or sputtering-like deposition. Through all that, the tool handles the moving on boundaries. So, for example, if you have a method on thermal expansion, it will kind of move the boundaries and adapt the mesh as it does the moving the boundary in the simulation. And finally, the tool is really good at generating all the mesh, pre-generating the mesh for you for these new volume that you deposit on the wafer. So, for example, you have kind of funky things that are being deposited, and it will all handle the mesh for you so that it's the best represented. So here I give so we get to the real life example. So this is a detector that was designed so in their RD50 times. So it was a MAPS detector that was with one of the foundries that was explored for MAPS. And in that case, so one of my PhD student, Ning Sin Meng, who did a lot of work on that. And we were quite lucky to have an NDA with the company, and that company had the full CMOS process of their foundry in TCAD files. So essentially, they give us a project with a CentOS project with all the tools, so essentially a workbench with everything to kind of make one transistor in their technology or a few different transistors. So what Linkson made. So she took this script, and obviously this was quite complex. As mentioned, it was like over thousands of lines of code. A lot of it was about preparing a wafer surface, and not everything was affecting what we were interested in, which is the electrical characteristic of these detectors. So she put these people were really nice, so they worked with her and sorting things out so they could understand exactly what she needed. In that process, as I mentioned, you had everything. So you were really doing the full CMOS processing, starting from a piece of silicon. It was defining all the gases, all the temperature ramp, so the thermal history of the device, ramping the temperature, keeping it, which gas is in the atmosphere while you're doing the applying the temperature. And then all the masks that were being used, applying the mask, so the interaction with the deposition of the photo mask or photo resist, implantation, etc., etc. And all that, that's the final result. So it was quite computing intensive because you do all these very complicated steps. And so they don't even fully simulate the photoresistor since it's kind of a symmetric structure. They only simulate half of it. So that's what we get out of the simulation. Very small, it's less than a micron wide. There's 20 mask step in there, and then you have the full thermal history, which at that time was not running on multi-threading, so it was quite long to do the structure. And what we wanted to simulate is something like the bottom here, so the Foundry, I guess the name is here. I can just say it. Which had like a stack that looks like this. So we had a deep N well that's connected through these ISO and an N well and N plus contact. Then we had a P substrate like just on top of the deep N well. So essentially this quadruple well structure. So you have NMOS and PMOS that are sheeted in their P well and N well and shielded from each other and from the substrate through the deep N well. So that's what we wanted to simulate. And so Linkson took essentially all the steps of the process, applied her own mask to the tool, and that's what she ended up with. So the structure that you see at the bottom here is essentially so we had one design structure that we were trying, very similar to what's on top, that we wanted to generate. She had a few little issues, so she had to sometimes go back and then do small bug fixes and such. And at the end, the most terrible is we, through mesh reduction, just to try to make it to run, we ended up with kind of a noisy surface because the mesh elements were too small, too big. And then, that's a lot of CPU power just to generate that one pixel detector structure here. So LinkedIn, so this is a slide from her at the time. She was trying to optimize that, but at the same time, we sat together and say, okay, that makes no sense. That it takes 40 hours to generate a rather simple 2D structure. Do we really need to do all that? Can we learn something from having the process simulation, having the information, but also do something that's more efficient? So what we did is we moved to structure simulation. I mentioned before there's these two different paths to making a structure. So there's one that's more geometrical and empirical. You just define what you have and what exists, and the other one really where you define how you build the thing that exists. So what she did is she got the off transistor process that I shown in the other slide. She extract the doping profile, so the interesting doping profile as function of depth that we needed, which is the part that you need to know a lot about what happened thermally in terms of implantation to know how these will look like. So she extracted that. That's the important information that was in these files, and she took that and then put that in the structure editor. And there I just explained a bit what the structure editor is. So it's a geometrical application, so it's very to use. There's a graphical user interface, so you can open it and even start clicking and build the structure. There's a circle, there's a tube, there's a cube. But it's also a scripting language, which for more serious simulation and such, at the end is probably good to script. But for example, you can use the graphical user interface, generate a structure, and the tool would give you the script that generates your structure. So then you can go to that script and modify things and start playing a bit more advanced way. You have advanced modeling, so you can see you can make really complex structure with like a complex geometric objects and such, and then you can define doping profiles in there, so you can place implant in your geometry, and it also has like a tool to do the meshing inside the same tool. It used this ACIS geometry kernel, so it's quite an advanced geometry modeling software behind under the hood, so that allows you to make, as I mentioned, quite complex structure. So you have the tool here. I show a bit what it looks like. So what you do is you define geometrical features, so squares mostly. In my case, I define the substrate, and I define these boxes here that are they're going to be becoming doping profiles. Then you define the material that are associated to each of these boxes, and you define profiles that are associated to the boxes. So for example, I can say, I want a Gaussian doping profile that's going to be evaluated inside that box. So you're not going to end up with a square doping profile. You're going to end up something that has like a Gaussian transition, but you define a region where this doping is applied or is painted on. So it's a bit similar like GN4 when you do things like that. Sorry. So as was mentioned, in these scripts that are coming out of the tool or that you can write, it's kind of its own little language. It's very similar to any programming language you've used before. So you can have strings, lists, arithmetic, and Boolean operation. You can write loops. You can make logical tests, procedural and system calls if you want to do something outside. And essentially, it's not the nicest, most good-looking language. Essentially, has a lot of parentheses and such. We would go through the scripts later, but rather easy to understand once you go down it. So this is again we go back to the work of LinkedIn. So this is the structure that we ended up when we were doing all the process simulation. And then the end, okay, it's a bit hard to compare because obviously the plotting tools and the scales that you use and such will affect a lot how it looks. But it gave us a pretty good structure with the correct doping profile at the different places we needed. But the nice thing is that it took 7 seconds instead of 43 hours to generate this one. Another way to do structure generation. So I'm just have a few examples there as well. You can do that. You can also take things that come from design. So you in that case, there was another design that was done in AMS, an HV CMOS process. It was a very small pixel. And in the center area, so here this was where you apply the high voltage, so we call it the P sub, the substrate contacts. And in the middle here was the pixels, the big N well, and inside there there's the P well and the N well, and then transistor that are inside that device. Sorry. So this is the structure that we wanted to design. We're interested in the breakdown. In that case, in that simulation, we were interested in locating where the breakdown occurred in the structure and try to see if there was any design help we could get from TCAD into avoiding that or making the breakdown go a bit higher so we can bias the structure more. So we got the GDS file again from the designer. So the designer could directly make his design and give it to us, and then we could run it through the process simulation or through a device generation script, but driving things directly from the GDS. And that works in both device simulation and in process simulation. So you can take a GDS file, load it, give names to the different layers, and can load that into your process simulation and use these masks as masks during your process, kind of in the abstract way. You say, okay, I apply this mask and I implant everywhere what that mask is not, or I deposit metal everywhere where that mask in. And then you can drive directly your simulation then directly from a design tool. So this is just one slide from Matthew. We did that work. So in that case, we explored also looking at doing 2D, 3D simulation, and then trying to see if there was difference when you go into 3D. So we had 3 structures simulated. So we had like a 2D full simulation where we had like every via, metal line, and wells in the structure, but it was still a 2D slice, in the middle of this pixel structure. Then we had like a reduced, so we removed all the via, we just got the minimum to bias the diode and the substrate. And then finally a 3D model that was kind of a reduced version of the 2D. This was created in the device, the structure editor. So in that case, you just use the mask to define the boundaries of the wells, the boundary of the contacts, and then essentially to define how the implants are being built in the device. And then I will show a bit more about it in the device simulation. What time is it now? Let me see.
8 minutes.
8 minutes. Well, I think I might stop here. And then next time we can go into the device simulation and the example. So I don't know if people have questions or they want to see a bit more from the examples that I have here, or if I can look a bit more in the Centers tool if you're interested in and go in a bit more detail.
Questions for Mathieu?
This was really useful, Matthias, because I'm coming from Silvaco, which is in some ways very similar, but in other ways very different. So a lot of the details of how these things are implemented are quite different. So it's useful to see. But I am kind of wondering, when you switch from the process to the device simulation, you go back to the process simulation to sort of double check that you get more or less the right answers from the device simulation, from the structure simulation?
Yeah, that was a bit that. I mean, my first approach was, okay, if we have all the process, it can be better than that, right? And I still think it's the case, but then with like infinite computing power. So that's mainly what we learned from that is the foundry. They're caring more about their thermal. For example, they quite detailed simulation of the thermal history of the wafer, which is done in simulation in great length. So out of the 43 hours, you spent maybe 30 hours doing thermal simulation. That we didn't need that like 100 and plus minus 100 nanometer level of detail for these big implants and such. So we said, okay, we can drop a bit of complexity by going to the device editor. We wanted the electrical field profile and such to be really realistic, so we still reuse the same doping profile, which is something we knew we could extract and kind of just paste into the device or the structure. So it's really, we just have a text file at the end that tells, okay, the n well is this value as function of depth. And when we did this device here, we would define what's happening here and everywhere from that text file. And we compare, so I did put the slide there, I could maybe put it next time. So when you compare both, it was quite matching quite well at the end, you know, for what we were looking at, which was where the breakdown is, what's the depletion as function of depth, and as function of bias voltage, that was working quite well.
And it looks like the shallow trench isolation was really not very successful. Is that that's again a function of the mesh size?
Yeah, there was like a lot of meshing issues. So this is not the last I took slide from her. You know, in the thesis, she goes a bit more in detail. I put a link there, so it will be in the slide. Yeah, the meshing was the big problem there, because since they're doing very detailed simulation, the mesh just in the like first 200 nanometer of the surface where the oxide is was very, very detailed, because they were tracking that in detail. They're building like bird's beak and such, so they care about what happens to the each NMOS and CMOS in there, NMOS and PMOS in there. We cared about, you know, the bigger structure, what's happening here, and eventually at the edge here and at these edges here. And in the case of Matthew, so in that case, we wanted to see where's the biggest electric field. Once we put like 120 volts here, 0 volt there, maybe I did, it's in the backup, but we add a metal line somewhere. So what happens is when you did the 3D simulation, we put all the metals that are not illustrated here in in this model, and you could see one line going over a well, and there was a really small spike of electric field there. And this was shown to the designer, and they modified that, and we did see the next batch that was produced, that the breakdown voltage went up by 10 volts. So that was kind of the use there to drive it from the design, so as to be able to, you know, still make sure that you have all the details there. So we would not have run all the, you know, metal 2, metal 3 metals there if we didn't have that method. We would just have to, if the diode does a contact to the diode, you know, and do this very simple thing here.
So yeah, okay, interesting. So you got the simulation from the foundry. It's
Yeah. We had to
that-
sign. We had to sign an NDA, which was L Foundry. I mean, I can say they were really nice. They gave us the whole thing as long as you sign, because most of them use the same tool. They use Centaurs, or also they have both. So they are, you know, if you're nice enough, I guess they're not always like that. You know, AMS and others, they didn't do the same. But sometimes, you know, you can go and measure. For example, for other foundry that didn't provide us as much detail, we could just take a piece and go do a sims or do some measurement to at least have something to drive your design.
Okay, so it pays to be nice to the foundry.
Yeah. Oh yeah. But I mean, I think you can do a lot without that, you know, because we learned a lot from. Yeah.
Good.
But for example, another good example, I'm gonna go into the device simulation the next time, and I'm talking about our jazz, and you know, how we went from that started like that. At the beginning, we were doing kind of our best guess. You know, there was back then, and there was people at CERN working on that, and you know, they got this good contact with Tower Jazz and such, and we started to look at the modified process, how to make it radar. And again, they were giving us a lot of information. You know, that obviously you sign against some NDA and such. When you publish, you cannot tell the number, but you can know at least what are especially like when you're dealing with EPIs and such, what is the resistivity there? You know, it's going to affect your depletion. It's interesting to know. Yeah.
I hope that we will be able to establish the same good relationship with with our foundry. Because otherwise I think would be almost impossible to do these simulations properly. Yes, we can have some guess here and guess there, but without
Well,
that
the
level of
thing is, okay, Tower Jazz for. I'm sorry.
yeah. No, without some level of cooperation with the foundry is not possible.
Yeah, I think at least a designer. So it helps a lot. I mean, already if you have a designer who has read the the whatever technological nodes manual, I did that personally. So with the AMS, with El Foundry, with our Jazz, I went and I signed the NDA to have the design kit. I'm not a microelectronic person, but I had the design kit manuals, so I could look what mask does what. You can look at the doping structure.
Yeah, but how long did it
there's
take?
lots of information.
How long did it take
Oh,
to do that?
Well, I mean,
We-
if you have a designer, right? Usually,
Oh yeah,
it
okay.
depends on the places you are. I think of it, but
Yeah.
I mean,
I was at CERN at the time.
we do have the design kit.
Yeah, so usually if you have a designer with the design kit, or usually, I mean, they would just depends a bit on your institution. I know National Lab would be a lot much longer to sign the stuff to get a design kit. If your university is probably simpler. But in general, they want you to get the design kit because they want you to buy a chip there. And there's a lot of information in there, which again, you cannot share or you cannot publish because you sign an NDA, but it's useful for you to know what's the stack, what's the thickness of the metals that they're using, what are the width of the diffusion, for example. In the design rules, sometimes there's hints about things. So yeah, there's all kind of clever way that you could go around having that great relationship. And that, for example, for Tower Jazz, that I will show next week. We didn't care so much about what was in the big P well, what the circuitry that was implemented there. We just made the assumption that we were pretty well shielded from the substrate. We have this big well, and everything is inside, other wells. So we're just gonna take care of having a big P well everywhere that we bias, having a backside that we bias, and the diode. And that was the most important in that case is the size of the diode, the distance between the P well and that diode, essentially, and the thickness and the resistivity of the substrate, because what we cared is to optimize the field under there. And that worked very well without having to put all the detail of the CMOS.
Yeah. Okay.
Okay, I have to leave. Thank you very much.
Yeah, thank you,
It's a
Mathieu.
pleasure.
Any more question for Mathieu? Otherwise, we meet again next week.
Perfect. Bye-bye.
All right. Thank you.
Thank you.
Bye-bye.
Thank you.
Bye-bye.